All right, in this video, we're going to be talking about section 2.3, part 2. We're going to be looking at some important theorems that come along with our polynomials. So first we have a warm-up. I'd like you to play along with me and give these a try. Part A, find all the zeros of f of x equals x squared minus 9. So that's simply asking me, I'll just come down here and do the work, saying that if we have x squared minus 9 equals 0, I would probably try to factor this to find the zeros. X plus 3, x minus 3 are the factors. So then I set each one equal to 0, of course. And I get x equals negative 3 or x equals positive 3. All right, so that part is done. Part B, what are the factors of f of x? All right, well, we just did that. So the two factors are x plus 3 and x minus 3. What would the remainder be if I were to divide f of x by x minus 3? Well, we could do it, but I know that x minus 3 is a factor of x squared minus 9. So I know that if I were to divide them, they're going to go in evenly, and therefore the remainder is going to equal 0. Okay, make sure you understand that connection, and I think you probably do. But since it's a factor, if I'm dividing by a factor, then that means there will be no remainder. All right, so what is f of 3? Well, we already determined that f of 3, right? F of 3 is a 0 of the function. Why is f of 3 a 0 of the function? Because it came from x minus 3 equals 0. And why did we care about x minus 3 equaling 0? It's because that was a factor. And since it's a factor, and we want to know when that factor equals 0, then what does that tell us about what f of 3 is going to equal? It's going to equal 0. And let's just do the math on that just to see it in action. 3 squared minus 9 is 9 minus 9. F of 3 is 0. Okay, so we need to look at the connection here between the remainder being 0, meaning it's a factor, and if it's a factor, x minus 3 that is, then we know that x minus 3 equals 0. Solve for that, and I get x equals 3 is a 0 of the function. So the remainder is 0. It's a factor. Since it's a factor, f of 3 is 0. So there is a huge connection between these two pieces, which hopefully you are well aware of at this point. Part E, what's the remainder if you divide by x minus 4? Well, I already know x minus 4 is not going to be a factor, so it will have a remainder other than 0. But let's find out what it's going to be. I'll use synthetic division. So for part E here, I'm going to do x, let's see, let me set up the box here. X squared minus 9 would be 1, 0, negative 9. And if I'm dividing by x minus 4, I'm going to use positive 4 here. I bring down 1, I get 4, I get 4, I get 16, I get positive, what, 7? So the remainder is 7. So now the question is, what do you get when you do f of 4? So f of 4, we've got f of x equals x squared minus 9. So I get 4 squared minus 9. I get 16 minus 9. Hey, look at that. 16 minus 9. I get 7. So f of 4 is 7. The same number I got as a remainder. Which brings us to our friend, the remainder theorem. Now, the way this is stated is kind of like not how we're going to use this most of the time. If a polynomial f of x is divided, well, actually, this is how we're going to use it. If a polynomial is divided by x minus k, the remainder is the same number you would get if you evaluated the function at f of k. So this does something for us. Now, the big question is, what is the primary reason for wondering about a remainder? And I hope that you know that the answer to that question is we want to know if the remainder is 0. because if the remainder is 0, then we know what we divided by is a factor. Why do we care about factors? Because factors help us solve polynomial functions. All right, so let's make sure we got this down. If you want to know what is the output when you plug in a number, you can obviously just plug it in old school, right? If you want to know what the value is at f of k, we can just plug the number in and get the answer. But another way we could get that same answer, right? It's equal to the remainder, is if you were wondering about f of k, we could divide by x minus k. And whatever the remainder is would be the same answer we'd get just by plugging in the number. All right. So I wanted to just connect this back real quick to what we had previously looked at, all of this information about real zeros of polynomial functions. So let's just cycle back to this one last time. You got a function, f of x. It's a polynomial. A is some real number, and f of a is 0. So I plug in a, I get 0. What does that tell us? Well, it tells us a is a 0 of the function, meaning, when I plug in that number, I get a 0 as an answer. X equals a is a solution to the polynomial function. Hey, when is the function equal to 0? So in other words, again, looking at it graphically, we know that a value creates a 0. We know then that x minus a is a factor of the polynomial. And we know a 0 is an intercept. What we also now know is if f of a equals 0, then the remainder is 0 if you happen to be dividing f of x by x minus a, which is a factor, which we already established. And we know if I divide by a factor, then there's going to be no remainder. Long story short, what this allows us to do is look at the remainder if I want to know if the output's going to be 0. And why do I want to know if the output is 0? Because that's usually how I'm solving equations. All right, let's stop the rambling and get on to some math. Okay, what would be the remainder when dividing this by x minus 4? Well, there's two ways to do it. I probably should have labeled this as f of x. So one way to do this is we could find, the answer. We could do synthetic division, x cubed, synthetic division, 1, negative 1, negative 14, and 11. And I would use a 4 here, right? The opposite, if I'm dividing by x minus 4, we use positive 4. So I could do that, or I could do f of 4, which would be 4 cubed minus 4 squared minus 14 times 4 plus 11. Now, this is where the remainder theorem helps us out, because I can do one much faster without the need for a calculator or anything else. I can get the answer super quick. And the answer is by using synthetic division. I can do this nice and easy. I can do it while I'm talking, and I can do the math pretty much without making a mistake, and I get 3. Now I come over here and I want to evaluate f of 4. I've got to do more thinking. 4 cubed is 64 minus 16. 4 times 4 is what? 16. Carry the 1. That's 56 plus 11. I'm going to add the positive ones together. I get 64, 75. Minus, I'm going to put the negatives together. 56, 66, 72. And I get the same answer, 3. So if you ever want to evaluate a function at a number, you could do it the old school way, or you could quickly do a synthetic division, which most of the time, unless the numbers get ugly with fractions, is going to be faster. This is what the remainder theorem does for us. All right, let's try one again. Example number 2, here's a function. Find f of negative 2 the, quote, normal way, and then find f of negative 2 by doing synthetic division. So part A, f of negative 2 equals 3 times negative 2 cubed plus 8 times negative 2 squared plus 5 times negative 2 minus 7. And honestly, by the time I get done writing this problem down, I'd probably be done with synthetic division. Not to mention now I got to do all the work. 3 times negative 8 plus 8 times positive 4 minus 10 minus 7, negative 24 plus 32 minus 17. Let's see. Negative 24 and 32 is going to be 8. 8 minus 17 is going to equal negative 9. F of negative 2 is negative 9. Let's now try it. Synthetic division. I'm going to write down a 3, an 8, a 5, and a negative 7. Make sure there's no missing terms. 3, 2, 1, 0. Nope, we're good. And I'm going to divide, I'm going to use negative 2. Okay? I'm going to use negative 2. So I get 3, I get negative 6, I get 2, I get negative 4, I get 1, I get negative 2, and I get negative 9. It is amazing how much quicker and easier that is. What does this tell us about whether x plus 2 is a factor or not? So if x plus 2 was a factor, then I would do division by x plus 2, which would mean I would take the opposite of plus 2, which is the minus 2, and I would get a negative 9 as a remainder. It tells us x plus 2 is not a factor. All right, so where are we going to be using this? We're going to be using this as a test. We want to know if something is a 0 or not because we want to know if something comes from a factor. So what we're going to be doing is testing a lot of numbers, and we could test them the old school way. Hey, if I plug in this number, do I get 0? Do I plug in this number, do I get 0? And that would be time consuming. Still time consuming to do that with synthetic division, but so much faster. Because, and this is sort of the, almost seems like I'm repeating myself, a polynomial f of x has a factor at x minus k if and only if f of k is 0. Okay, using the remainder theorem, that's also telling you when I divide it, the remainder is 0. So this is kind of a no-brainer, but this is known as the factor theorem. Kind of just ties all this together, looking at all perspectives. All right, how are we going to use this stuff? Let's go. Example 3. Use the remainder theorem to evaluate the following function at x equals negative 3. All right, so this is really just one more practice. So I'm going to evaluate this not by plugging in negative 3. I'm going to evaluate it by doing synthetic division, and I'm going to use negative 3. 2, 7, negative 4, negative 27, negative 18. Bring down the 2. I get negative 6. I get 1. I get negative 3. I get negative 7. I get 21. I get 6. That's negative. I get positive 18. I get 0. All right. So the remainder is 0, which tells me f of negative 3 equals 0. So what have I learned from that? Let's put it all together. I now know that x plus 3 is a factor. I know one of my zeros, right? 0 is x equals negative 3. I know this thing has an x-intercept at negative 3, 0. All of the meanings that this has. So this is why we're talking about it, because I'm hunting for numbers that will make 0. All right, let's keep going. Example 4. Show that x minus 2 and x plus 3 are factors of this. Okay. So I could do this one of two ways. I could use the remainder theorem the bad way, and I could say, hey, if I do f of 2 and it equals 0, then we know it's a factor. Okay. Not going to do that. What am I going to do? I'm going to use synthetic division. 2, 7, negative 4, negative 27, negative 18. All right. Is x minus 2 a factor? Let's find out. I'm going to use positive 2. I always use the opposite. I get 4. I get 11. I get 22. I get, what, 18? I get 36. I get 9. 2 times 9 is 18. I get 0. All right. Now, yes, x minus 2 is a factor. So now the question, what do I do with x plus 3? Well, I could go back and I could redo from the start and just redo this again, but use a negative 3 instead. But I don't want to do that because I want you to think about this real quick. Let's ask this question. I'm making this up on the spot, so hopefully this works out okay. So show that 2 and 5 are factors of 100. Okay, so same basic question, right? Show that two different numbers are factors of a bigger thing. So what is the equivalent of what I just did? I just did 100 divided by 2, and I got 50. I got no remainder. And so yeah, no remainder. I found, yes, 2 is a factor. So I could do one of two things. I could go back and now do 100 divided by 5. Does that go in evenly, or is it a factor? And that would be yes, it's 20. But if 2 and 5 are factors of 100, then that means I could break them down further by not starting over. I could look at the answer. So if 5 is a factor of 100, it's also going to be a factor of 50. So I could, instead of doing this, I could have said, all right, let me test this one. 5 goes into 50. Yep, 10 times. So it is a factor of 100. And therefore, like, why do I care about this? Because this is how we're going to end up factoring a polynomial that's unfactorable. So what I'm suggesting is what we do at this stage is we just keep on going. We take this factor and now we break it down. So I'm going to take negative 3 and bring the 2 down, negative 6, positive 5, negative 15, 3, negative 9 is 0. All right, so let's summarize what we've done. I took this problem which I have no idea how to factor, and I factored it, or I showed that x minus 2 is a factor, and the other factor that goes with it would be these numbers right here. So it would be 2x cubed plus 11x squared plus 18x plus 9. And then what I did was I said, all right, well, this factor down further. So I divided it by x minus 3 and turned it into 2x squared plus 5x plus 3. I'll bring this one down. So I've taken something that I didn't know how to factor, and by just having sort of a starting point, I was able to factor it to this, and I took this one and factored into this. And now, since this is a quadratic, I'm going to try to factor it further. I've got 1 and 2 and 1 and 3. I need to add to be a 5. So I'm going to do x and 2x, and I'm going to do 3 and 1, both of them plus. I get 2x squared, I get 3x, I get 2x makes 5x, and I get 3. That tells me that this is going to factor all the way down into this. All right. So that is why I want to keep going, because then the problem gets easier and easier, and this is how I end up factoring something all the way down. All right. I hope this is all making sense without anybody looking at me like they're confused. It's hard to know to keep rambling or move on. So I'm going to move on. Use what you found in example 4 and what you know about polynomials, and now provide me a sketch of f of x. All right, so what do I know about polynomials? Let's take a look at this thing. Where is it? There it is. I can see it. Okay, the degree I'm just going to make a list. Degree is 4. More importantly, that makes the degree even. So now I know my end behavior. X goes to infinity, y goes to infinity, x goes to negative infinity, y goes to infinity. Leading coefficient, I should have included that in that discussion. I just sort of glossed over it, but the leading coefficient is positive. It's positive. So those two things together lead me to that result. I have a y-intercept is 18, negative 18, excuse me. And because I did all this stuff to factor it, I know the zeros of the function are x minus 2 is a factor. So 2 comma 0 is a x-intercept. And 3 comma 0 and negative 1. And what is that? Negative 3 halves. Multiplicity of each is 1. All right, let's throw it on a graph and see what happens. Y-intercept down here at negative 18. I've got a 2, I've got a 3, I've got a negative 1, and a negative 1.5. I'm going to end here. I'm going to end here. And since the multiplicity of each of my factors is 1, that means I'm going to pass through all these zeros. So my graph should come down, come up. Something's wrong. What did I do wrong? Let's go back and find it, because clearly something is wrong right here. All right, I passed through 3, passed through 2. Let me check my math. Something's not right. Ah, there it is. This was supposed to be x plus 3. Did not catch that before. So that means this is not correct. I've got a negative 3. All right, and you can see how all these things work together and they can help you catch errors. All right, now let's try it again. I'm passing through the 2. I've got the intercept at 18, passing through, and ending going up, and it all works together. Okay, we'll go ahead and stop this video here, and we'll see you for part 3 on the next one.